Hello everybody and welcome back to another video. My name is Codenaddicts, and in today's video we're gonna go over this really interesting, is probably the best way to put it, bronze problem called milking order from the 2018 US Open contest. And so hopefully you all have taken some time to read the problem statement before watching this video. If you haven't, pause now, the problem statement's right here. Read through it, and when you think you've finished reading or you think you got the solution, come back and we'll work through it together. Okay, so essentially we've got n cows, and there are two constraints that we've got on these cows. The first constraint is that the cows have a hierarchy. So for instance, cow 3 can be higher than cow 2 and cow 2 higher than cow 5. And moreover, this hierarchy is linear. So that means that if cow A is greater than cow B and cow B is greater than cow C, then we know cow A must be greater than cow C. And moreover, there's no two cows of the same hierarchy, of the same status. And then one other thing is that Farmer John's and cows need to be milked, and that leads us to the second constraint, which is that certain cows can only get milked in a specific spot. So Farmer John's goal right here is to order the cows in a way such that he can milk the cows in that order, and it satisfies these two constraints. So for the first constraint, if cow 3 is greater than cow 2 greater than cow 5, then cow 3 would need to be milked earliest, and then cow 2, and then cow 5. And in the second constraint, certain cows need to be milked at certain spots. So for example, cow 4 might insist on being milked second among all the cows. So those are the two constraints. And the last thing, what we're actually trying to figure out, is the soonest that cow 1 can get milked. And so here's our sample input. Let's get to work on taking a look at this. So 6, 3, 2, we know that we've got 6 positions, so let's take a look at that. We're going to draw position 1, position 2, position 3, position 4, position 5, and position 6, and I'll label them accordingly. So 1, 2, 3, 4, 5, 6, and we have these two constraints right here. The first constraint tells us that 4 is greater than 5, 5 is greater than 6, and the second constraint tells us that 5 is fixed in position 3 and 3 is fixed in position 1. So let's handle that second constraint first. We're going to fix 5 in position 3 and 3 in position 1. And now we've got to place 4, 5, and 6. We know that 4 must be greater than 5 and 5 must be greater than 6. So what can we do here? Okay, well, here's the thing. We know that we want to place 1 as soon as possible, as left as possible. So what does this tell us? This tells us that if there is something before 1 and it can go after 1, we should place it after 1. So that's exactly what we want to do here. We want to see, is there anything which is before 1 and can be placed after 1? So we can actually generalize this. We can say for anything which we know can possibly be to the right of 1, place it to the right of 1. So obviously ignoring here these constraints because they're fixed, we're left with 4, 5, and 6. Now all of 4, 5, and 6, we know that it might, well, we don't know, but it might be possible for them to all be placed to the right of 1. So we want to try and do that. We want to try and place them as far right as possible. So when it comes to 6, we can obviously place 6 in position 6, right here. And when it comes to 5, we can, oh no, we can't. We already have 5 right here. So 5 will go again right here because 5's position is fixed. And then we have to place 4. Now remember, we can't place 4 here because 4 must come before 5. So we need to place 4 right here. Now, of the 2 remaining spots, is there any constraints for these spots? No, there isn't. So 1 can go in either of these spots, and so obviously, naturally, we're going to place 1 right here. So you got 3, 4, 5, 1, and then this would force 2. But we don't really need to care about that. So in this case, our answer would be 4. But there's some things we've got to be concerned about. The first of which is, what if 1 is fixed? So what if we had 1 is fixed in position, I don't know, 5, for example. Then we couldn't place 1 and 4 because 1 would have to be fixed in position 5. But if 1 is fixed, I mean, it's not going anywhere. There's no reason to actually do all of this work. So if 1 is fixed, we just output the position it's fixed in. That's a pretty simple edge case. But let's think about a different edge case. What if in this 4, 5, and 6, and I'm going to use a different nice deep purple, what if we had 4, 5, 1, 6, or something like that? Or we had 4, 5, 6, 1. If we employed this algorithm, we would end up having 1 here, 6 here, 5 here, and 4 here, and we would have chosen 4. But we can't choose 4. We shouldn't choose 4 because 1 we placed here. So we would choose 6. But hold on. Why should we place 6 in position 5 if 1 is going to be after 6? It would make more sense to do this. It would make more sense to place 1 here, 6 here, 5 here, and 4 here. That way we could have 1 in position 5. So that leads me to my second edge case. If we know that something is to the left of 1, and that can only occur if 1 is in this thing right here, if we know that something will be to the left of 1, place it as far to the left as possible. Because if we place it to the right and it can go to the left, then we're removing the amount of spaces that 1 could possibly get. If you don't understand that, take a bit and think about it. It should come to you as semi-logical. And once you get experience with greedy algorithms, you'll be able to intuitively understand why this works. It also might be easier for you guys if we work through it in code. So let's do that right now. Here I have Visual Studio Code open with milkorder.cpp, milkorder.in, and milkorder.out. We're going to get started off by doing hashtag include bits/stdc++.h and using namespace std, and then we're going to have an int main file. In this main file, we're going to need to open up milkorder.in with read, and this is in Python, so we're going to have to use double quotes. Into stdin. And we're going to need to do this as well for out. And we're going to need to write. Okay, so one thing to note, in the newer versions of USACO, you won't need to do this because you'll get the input directly from stdin, and you output directly to stdout, or stdout. And now what we want to do is we want to read our input. So we've got n, m, and k, so let's read those in. Int n, m, k, sin, n, m, k. That is not k. There we go. And we get let's keep track first of a vector of int r, array of size n plus 1. So what does r represent? R represents our tracking of where each number goes. So for example, R of 3 would be 5. You might be wondering, why are you doing n plus 1? That's because, remember, vectors are 0 indexed, but we want to start from indexes 1. So we've got to keep n plus 1 so we can access that index as 1. We also are going to want to keep track of a vector of int fixed array of size n plus 1. What's this going to do? This is going to be, essentially, if one of our cows, if any cow, is fixed in a position, we want to know what position that is. And remember, that's for this part of our algorithm, the one where we jump from 6 all the way to 5, right here, because we know that 5 is fixed. So that's that part of the algorithm. So we need to keep track of that in a fixed array, so that's what this does. And you might be wondering, well, what about the indices where it's not fixed? For those indices, it's going to simply be 0. And 0 is not an index that's valid in our case, so we can just ignore that. Okay, so now we want to take a look. Let's see, what are we going to do here? We're going to keep a vector of int, let's call this high, and this is going to also be of size n plus 1. No, this is going to be of size m. And vector of int high is going to represent our hierarchy, so let's read this in. We're going to use for int and I in AGI, sin I. And we're going to need to start reading in our C's and P's, our cows and their positions. So for int I is equal to 0, I is less than k, I plus plus, int CP, sin CP. We're going to want to say fixed of C is equal to P, R of P is equal to C. So now we fixed these. Now it's our first case. If fixed of 1, sout fixed of 1 slash n returns 0. Okay, so what's this doing? This is just briefly this fixed of 1. If it's greater than 0, then we know that we have set this fixed of c equals p, which means 1 is fixed, cow 1 is fixed, and so we just output that. And if it's equal to 0, this if condition won't activate because 0 is falsy. So now what we're going to do is we're going to start going backwards through our array to try and place our hierarchy from right to left. So we're going to say int ptr is equal to n for int I is equal to m minus 1, I is greater than or equal to 0, I minus minus. I'm going to say int cur is equal to hei of I. Okay, so here's the interesting part. If cur is equal to 1, this means that 1 is part of our hierarchy. We don't want to go from we don't want to go right to left anymore. We don't want to go rightwards. We want to start going leftwards. We want to start placing as left as possible. But we want to make sure that we're not placing cur in a spot that something else should have gone. We're not placing 1 in a spot something else should have gone. So we're going to have to restart from the beginning of the array. So I'm going to say pointer is equal to 1. I'm going to say for int j is equal to 0, j is less than or equal to I, j plus plus. And what I'm going to say is cur is equal to hei of j. If fixed of cur, and this is just essentially what we've been doing here, or what we're going to do later. Actually, I should clarify what we're going to do later, but let's set this for now. This is going to be if fixed of cur. Okay, so let me explain what's going on here. If cur is fixed, if our current value is fixed, we're going to want to jump to that. So what I'm going to do is I'm going to say pointer is equal to fixed of cur plus 1, because remember, we're going to start considering after cur, and I'm going to say continue. Now, if it's not fixed, we're going to say while r of pointer plus plus. So what's this doing? This is essentially checking if we already have some value in r at that index, we need to keep going. And now what I'm going to say is I'm going to say r of pointer is equal to cur pointer plus plus. And now, after we finish executing all of this, I know that I'm going to have just considered pointer is going to be the index just after 1. So I want to output pointer minus 1 and return 0. And now, if cur is not 1, then we keep going from going right to left. So I can just actually copy this code right here. But instead of plus 1s, we're going to do minus 1s. And we're going to do minus minuses and minus minuses. Brilliant. And now what I'm going to do is I'm going to say for int I is equal to 1, I is less than or equal to n, I plus plus. If r of I is equal to 0, sout I slash n return 0. Okay, and there we go. That's it. So let's test this. What I'm going to do is I'm going to run g++ minus std equals c++ 11 minus wall minus o2 milk order.cpp minus O, milk order. And this is going to compile the file. And I'm going to run ./milk order. And milk order.out is 4. Brilliant. So let's switch back over to our USACO tab. And I'm going to submit milk order right there. And submit the solution. And there you have it. All correct. So I'll just quickly go over the code one more time. Here it is. Essentially, we just read in our input, kept track of an array, kept track of everything that was fixed, and we checked if one is fixed, and if it is fixed, we outputted it. We tried to go from right to left, but then we noted that if cur is equal to 1, that is, if 1 exists, everything before it needs to be placed as leftmost as possible, so we place it as leftmost as possible. And then if cur is fixed, and this is basically outside of this if cur is equal to 1 clause, if cur is fixed, we simply try and jump to the one right before cur, and then we check is if the r of pointer exists, we say pointer minus minus, and then r of pointer equals cur, pointer minus minus. And so this essentially just handles placing the current value and decreasing pointer. And now we check, is any value equal to 0? The first value that's equal to 0 is the first spot we can place 1, and we output that and return. And that's it for this problem. I sincerely hope that you all enjoyed this video. It was a real blast to make. This is actually my second take recording this, and this problem is very fun, and I hope it's taught you guys a lot about greedy algorithms and has improved your CP skills overall. If you guys do have any other questions that you want me to solve, problems you want me to solve, or just anything, let me know down in the comment section below. Don't forget to like and subscribe, and I'll catch you all in another video.